Hello and welcome to another video from HPart. Today we will be discussing the design of Cooke Triplet lenses. We'll be using Fresnel, which is free optical design software available at h-part.com. The Cooke Triplet lens can be considered the first modern camera lens. Designed back in 1893, it's still commonly used today. It's a simple lens design that uses just three lens elements: a biconvex crown, a biconcave flint, and another biconvex crown to balance out all five cidal aberrations. That's spherical aberration, coma, astigmatism, field curvature, and distortion. Today we are going to design the Cooke triplet that you see now. This Cooke triplet is a narrow field lens with a focal length of 20 millimeters, an f number of 3.5, and it's designed to image this narrow field onto the IMX297, which is this camera sensor over here. And this is the camera sensor that's common in Raspberry Pi cameras. So you could imagine doing this design as a narrow field machine vision lens for, say, a Raspberry Pi application. So now that we know what we're setting out to do, let's get started. The first thing we're going to do is perform some initial calculations to get an idea for the diameter of the lens elements that we're going to use. So I'm going to open up a workbook, call it Basic Design, and I'm just going to start with the dimensions of our sensor, which is the IMX297, and it has a width of 4.97 millimeters and a height of 3.73 millimeters. That gives a diagonal of about 6 millimeters. Now we want a focal length of about 20 millimeters, and we want an f number of about 3.5. Now this gives us a pupil diameter of roughly about 5 millimeters. Now I'm going to want to choke that down a little bit to give me some better sharpness, so I'm going to go for an aperture stop of about 4 millimeters. And once I know that, the other lens diameters fall out, so a rough biconcave, the center lens diameter is going to be 6 millimeters, and then the larger outer lenses, the biconvex lenses, those will have diameters of about 8 millimeters. So now I have a rough idea of how big the lenses are going to be in diameter. So now I'm going to go ahead and create them. So I'm going to start with the BCX lens. I'm going to make that 8 millimeters in diameter with a center thickness of 3. Put it at the origin. And as far as the material, I'm actually going to go for INLAC 9 in this design, which is going to allow us to have a little bit better performance than in BK7. Similarly, I'm going to use NSF4 for the central flint lens. Again, that just gives us a little bit better performance. Go ahead and create the first crown element. Then I'm going to create the center flint element. That's going to be within SF4. There we are. And I'm going to put that out at about 4. Okay. And then I'm going to create the final element, which will be BCX. It will have a diameter of 8, center thickness of 3, and that'll be about 6. And we're going to go with INLAC 9. And I'm going to put that there. That's fine. Oops, probably want to bump that out a bit. All right, perfect. All right, now the next thing we need to do is create our detector, which I'm going to put out at 20. Probably too far out, but so be it. Rotate it so it's looking down the optical axis. All right, there's our detector. Now I'm going to create our detection, which will be rectangular because it's the image sensor. So 4.97, 3.73, just like before. And there you go. You can see we've got our image sensor over here. Okay. Now the next thing I'm going to do is I'm going to set all these distances with spacings rather than the absolute coordinates that we're using right now. Open up the formula, and S12 is going to be spacing between 1 and 2, and I'm going to set that to about I don't know, 3 millimeters. That's pretty far, actually. I think I'm going to go for 1.5. That looks better. And then I'm going to choose another formula, spacing, S23. Okay. And drag that into position. Now I'll do the detector spacing. 3D. Detector. And I guess we'll go with 6 for now. Probably needs to go a little bit farther out to give us our focal length, so I'm actually going to increase that to 10. Okay, that's looking pretty reasonable. Now the next thing I need to do is I'm going to put the aperture stop in. So I'm going to create the aperture. It's going to have a diameter of 4 millimeters. The aperture itself will be a 10 by 10 box, and I'm just going to put it kind of around 9 right now. That's a little bit farther out. We actually want it in front of this lens over here. So now I'm going to use the spacing to get it in roughly the right position. We're going to have to tune this a bit. Aperture initial spacing, 0, okay. So now it looks like it's in the right spot, but really the origin of the plane, which is right here, is actually touching the end of the center thickness. So as the lens curves up like this, it's actually going to come into the aperture, which we don't want. So we actually need to offset this by the sag on the right side of this lens. So I'm going to go ahead and edit this formula. I'm going to rename it to S2D. And then I'm going to use the right sag. I'm going to call that sag A. And I'm going to add that. As you can see right now, that's very small, only 90 microns, but it will get bigger when we optimize it. So that shifted it over. And now we're looking pretty good. So now, before we add the emission, I'm going to create the light path. Make this a little larger. Zoom out. All right, left surface, right surface, left surface, right surface, aperture, left surface, right surface, detector. I'm going to double check it. Left, right, aperture, left, right, detector. Good. All right, now we need an emission. So here we're going to use an infinite grid emission. Essentially what that does is it simulates rays coming in from infinity at different angles to form a grid. And this allows us to optimize the performance of the lens by looking at a grid of spots on the detector rather than having to consider, say, an infinite number of points or a only two-dimensional ray fan or something like that. So go ahead and create our infinite grid emission. Again, this is a narrow field optics, so we're only going to have a 10-degree field here. We're going to have a single wavelength, 550. We're going to increase the rays so that we get, say, 400 rays per point. And we're going to set our light path. And it's already picked body 1 as the target. Now I'm going to create that, and I'm going to cast it. And here we go. So now we've got a bunch of rays coming in from infinity, traveling through our first element, through our lens, and onto our detector. But as you can see, none of these rays are focusing. When we get this system into focus, you're going to see a grid of focused points, which match the grid of angles this infinite light is coming in at. All right, so now that we've got the basic system set up, we need to optimize it to bring this emission into focus. In all the videos to date, we have used ray tracing analyses like collection efficiency or spot size in our optimizations. However, for lens systems, especially for more complicated lens systems, it's a better idea to first perform a paraxial optimization before you transition to a ray tracing based optimization. Explaining how paraxial analyses work is a bit beyond the scope of this video, but suffice to say that they are much faster to compute than full ray tracing based analyses. However, they tend to be approximate. So they're very useful for quickly getting the optical system into the right position. And then after you do that, you would create a ray tracing based merit function and then fine tune it with a ray tracing optimizer, which would be slower but more precise. So let's go ahead and create a paraxial analysis. Our first one, we're going to scroll down. If you look at the analysis menu, you can see we have a lot of ray tracing analyses, but at the bottom we have our paraxial analyses. The first one we're going to create is the ABCD matrix analysis. This is going to generate an ABCD matrix for our optical system. Now what's useful about this, and I'm just going to quickly run it, is that it will allow us to quickly bring our system into focus. So for an infinite conjugate system, i.e. a system that's imaging objects at infinity, the A term in the ABCD matrix should be near 0, and right now we are very far away from 0. So that's our first analysis. Our second analysis is going to be the principal planes. Now this is going to give us a lot of interesting information. Our effective focal lengths and where our object and image planes actually are. Now we want an effective focal length of 20 millimeters, and we are way over that right now. The next analysis that we're going to create is actually going to be the working F number. And remember, we want this to be 3.5, and right now we're up at 9.4, so that's not very good. And then finally, and perhaps most importantly, the sidal aberrations. These are approximate calculations that measure the aberrations that exist in our optical system and that we want to minimize. So let's go ahead and create that and run it. You can see these are all fairly large aberrations right now. Okay, so we've created a suite of 4 paraxial analyses, and now we're going to build a merit function. So first we want term A, then we're going to the principal planes, effective focal length, then our working F number, and then we want all the sidal aberrations. So distortion, spherical aberration, coma, astigmatism, and field curvature. So those are the 5 sidal aberrations. And then we want to add the optimization variables. So we're going to allow all the spacings to be adjusted except the aperture spacing. All right, and then we're going to want all the radii to be adjustable. So there's 1, 2, 3. Okay, great. So now we're going to go ahead and set all the limits. And this is very important because the optimization or the merit function over a complex system like a lens has many peaks and many valleys and many local minima. So the more you can restrict this and get towards get in the area of a solution, the faster and better the optimization is going to work. So we're going to tighten all of these up. We don't want to be any closer than 1 millimeter, and we probably don't want to be any farther away than 3. And the detector spacing probably shouldn't be any closer than, say, 5, and shouldn't be any farther away than 15. Now, as far as the radii here, some of these are actually going to end up being flat, so I'm going to allow them to go up to 1,000, which is effectively flat. And then for the minimum radii, I'm just going to allow them to go down to slightly more than half the diameter of the lens. So this is an 8 millimeter diameter lens, so I'm going to let this go down to 5, which is slightly more than half of 8. This is a 6 millimeter lens, so I'm going to go down to 3.5, and then 5 on both of these. And we'll make that 1,000. All right, excellent. So now I've got everything configured. I'm going to go ahead and create that merit function, and I'm going to calculate it just to see how we're doing. Okay, great. So now we need to set our target and our thresholds. So our ABCD matrix, our target is 0, and our threshold is 0.1. Hopefully we'll do a lot better than that. Our target for effective focal length is 20, and I'd like us to be within, say, 0.1 of that. Our goal for the F number is 3.5. I'd like to be within 0.1 of that. And our goal for the site elaborations, we'll just have it be 0.01 for all these. And of course, we'd like them to be 0, but I'll be happy if they're 0.01. Okay, so this should be both sides of the target, both sides of the target. This should also be both sides of the target. All of these are fine as they are. Okay, excellent. So I'm going to go ahead and save that. Now the next thing we need to do is create an optimizer. CMAES is fine, though others would also work. We'll go with sequential. We're going to crank up the number of max evaluations. And now we're going to move this over here. Zoom out just a bit so that we can see it. And we're going to run the optimizer. And away we go. So you see it's doing all sorts of crazy things. It's kind of scrunched everything together, but it should recover after a moment, he says. All right. And you can see we're continuing to drop pretty quickly. This is getting spaced out nicely. And we seem to have roughly flatlined right about here. So this is a reasonable initial design. To see it, we can run the infinite grid emission, and you'll see that it's starting to focus, but we're still a little bit out. So let's take a look at our merit function. As you can see, the A term here is not doing very well, but all of our site elaborations have been reduced dramatically, and we're doing pretty well here. So let's take a look and see if we're running up against any of the bounds. So we're definitely running up against this one, and it definitely wants to move this out as well. So I'm going to take a look, see if we are up. Nope, we're not up against any of these other ones. So I'm actually going to let this one go out a bit because this is, I think, the most important constraint here. And then I'm going to rerun the optimizer and see if we get some better results. All right, well, that's a lot better. You can see that it is basically dropping to 0, and now it's converged. All right, wonderful. So now let's go ahead and recast. You can see that we're focusing now right on the detector. This is looking pretty good. These aren't too far apart. They aren't too close together. And now let's take a look at our merit function. And this is looking really good across the board. We're matching up. We've got very low site elaborations. We're right in focus. Effective focal length looks good. Our F number looks good as well. So we've done a great paraxial optimization here. And now the next thing we need to do is we need to fine-tune it with an actual ray tracing based analysis, merit function, and then optimization. So let's get started by adding the analyses. First analysis I want to add is collection efficiency. We're going to filter the stray rays. This is going to measure how much of the light is actually making it to the detector. The next one is spot size. This is going to give us a sense for how good we're focusing the light, how well we're focusing the light. The next analysis I want to add is going to be grid distortion. Then I'm going to add field curvature. And then I'm going to add RMS wavefront error. This is going to go very similar to spot size, but is a little bit finer grained. And then finally, relative illumination. So now that I've created these 6 analyses, I am going to run them one at a time. Okay, good. So now there we go. So we're getting about 32% of the light, 33% to our detector, which is a good start. Hopefully we can get that up a little bit. Then the next one is spot size. So let's go ahead and run that. Our spot size is about 100 microns. That's not very good from an MTF perspective. We're certainly going to do a lot better than that with the fine tuning. But we can click on an individual cell to see how each grid point is doing. You can see The area diameter is about 2.6 microns. That's the blue circle in the center over there, and the red circle is our actual spot size. You can see we got quite a lot of room for improvement there. Okay, the next one is our grid distortion. This looks really good already. So you can actually tell from the dots here that they are forming a nice uniform grid. So I'm pretty happy with that. Check, make sure filtering stray rays. We are. Field curvature. We can get this a little bit better. You can see, if you just take a look at the dots here, you can see them bending. This is our field curvature. And I think we can tighten that in quite a bit. And then, of course, the RMS wavefront error. This is quite large at 0.8 waves, and this is related. You can just click on an individual one, and you can see the wavefront error here. We're going to bring this way down when we focus it. And finally, the relative illumination. This is already very good, which means we're uniformly illuminating our detector. All right, great. So now that we've gone ahead and added the different ray tracing based analyses, next thing we need to do is create a merit function for them. So we're going to start with the one paraxial analysis that we'll actually use here, and that's going to be the effective focal length. So we still want that to be 20, just as it was in the previous merit function. However, the F number we can actually get through a ray tracing analysis. So let's go ahead and actually create that one now. We're actually going to get it out of the image numerical aperture. So we're going to create that analysis right now. And I'm going to drag that up here and run it. You can see we're very close to the F number we got paraxially, but it never hurts to do it with ray tracing if you're already ray tracing. All right, excellent. So now we'll add that one next. So there's our F number. We want that on both sides of the target. 3.5, 3.6. Okay, great. So now we'll just keep working our way down. The next one is the collection efficiency. We want the soft collection efficiency. Obviously our target is 100. That would be great. And we're already at 35, so maybe we could get up to, I don't know, 40%. And then the next one is the grid distortion. And this one was already, we were already doing pretty well on this. We were at, was it 0.28%? That's not bad. We'll see if we can get that down to our target should obviously be 0, but good enough would be 0.1. And of course, it's above the target only. Then the next one is field curvature, best focus. Let's see where we are on that now. 0.18. Obviously, we'd like the field curvature to be 0, but 0.5, that would be pretty good. All right, next one would be the RMS wavefront error, which targeted would be 0, but I would be happy with 1/20th or 0.05. And then finally, the relative illumination. The RI ratio, goal of this would be 1, 0.9 is good, and we're actually already there. So that'll be good. Both sides of the target. All right, excellent. So now we've added all of the different analyses that are going to make up our merit function. Let's go ahead and check. We have collection efficiency. Looks like we're missing spot size, grid, field. Okay, everything is there except for spot size. So let's go ahead and add spot size. All right, excellent. So I think our goal here should be around 3 based on what we saw from the area disk when we actually manually looked at the spot size. I'm going to drag that up so it's right below collection efficiency. Recalc. Okay, that looks good. So if we take a look here, it's spot size and wavefront error are our 2 biggest costs, which makes sense because we've got a ways to go on dialing that in and getting diffraction limited. Now let's go ahead and add all the optimization variables. These will be the same as they were for the first merit function. All the spacings except the aperture spacing. And then one right left. let's just keep adding these radii. Okay, we're almost there. Okay, great. Let's go ahead and we're going to put some constraints on them. All right, so that'll be up to 3, 20, 5. Okay. And then our curvatures. First, I'm just going to enable these all, and then I'll go in and set them. So just a little bit more than half. And then up to 1,000. And a little bit more than half. 1,000. All right, getting closer here. A little bit more than half, and up to 1,000. All right, excellent. And now the last one was this one. Be a little bit more than half. And then finally up to 1,000. Okay, that all looks good. We've added all of the terms. We've configured them all correctly. Yep, they all look good. Save that, calculate it. We're not violating any of these. Well, we seem to be violating that one a little bit, but hopefully we'll tighten that up a bit. All right, excellent. So now I've created our ray tracing merit function. Now I'm going to go ahead and create the optimizer. Same idea, sequential. I'm going to open it up to a lot of evaluations in case we need them. And I'm going to zoom out on this guy. And I'm going to drag him to the bottom right so we can see it as it runs. And now, moment of truth, I'm going to run the optimizer. All right, now it might take a little bit before it starts really dropping because it has to break out of the basin we were in from the paraxial optimization. But yeah, there we go. It's starting to break out. So we started at around 60 and we're already down at about 18. We'll see where it ends up stopping. All right, it seems we've stopped around 10 1/4. I'm going to go ahead and put a stop to that one, and let's take a look at the merit function. Okay. So our F number is pretty reasonable. We're close enough on our focal length. Our collection efficiency fell a bit. Our spot size, however, has dropped dramatically, down to about 6 microns from where it was before. Grid distortion looks good. Our field curvature looks much better. Our wavefront error has fallen greatly. We're now getting much, much better results there. We are really violating this bound right here. And we could add a weight to this to make this perform a little bit better. And we're also pushing this bound as well. Everything else looks pretty reasonable. So I'm going to just see if we can make this a little bit better by letting this spacing increase a bit, because I don't want to let this get any closer. So I'm going to go ahead and increase this to 5. And then I'm going to rerun the optimizer. Now it may take a little bit before it starts breaking out of that basin and using the degree of freedom that we gave it. Nope, it doesn't look like there was any better solution even though we widened the range for that spacing right here. So I'm going to go ahead and stop the optimizer. So now we've got a optical system that looks like it's doing pretty good across the board and across the different parameters that we care about. However, we'd like to get a better sense for how it will actually perform on the image sensor. So to this end, we're going to create a new kind of analysis. This is going to be called the PSF-MTF analysis, or point spread function / modulation transfer function analysis. But before we can do that, we're going to have to create another emission, because the PSF-MTF analysis needs a lot of rays. So let's go ahead and create a new infinite grid emission. It's going to be exactly the same as our first one, except it's just going to have 10 times as many rays. So first one had 10,000 rays. Here we're going to use 100,000 rays. And that'll work. And we're going to go ahead and create our PSF MTF analysis. Stray rays, sensor Nyquist, 3.45. And we'll use Infinite Grid 2. And, oh yes, we also want to put a light path on this. All right, excellent. So now I'm going to run the analysis. And away we go. So it's going to take a little bit of time to compute, but even as these rays fill in, we can start to analyze them. Now, we don't have as many as it would like, but I think we have enough. So let's go down and take a look at what we've got. First, this is the point spread function, which you can interpret as the image of the spot for this particular grid point. And computed from this is the modulation transfer function, which is what we're interested in. This dotted line here is the Nyquist frequency, spatial Nyquist frequency for our image sensor. Basically, anything beyond this doesn't really matter because our sensor can't resolve it anyways. Now, the way to interpret a modulation transfer function is to first consider the different spatial frequencies. From about 0 to 30 cycles per millimeter is roughly coarse detail. 30 to 60 cycles per millimeter would be medium, and 60 to 120 is roughly fine, and above 120 is where you start to run into the Nyquist frequencies for your different image sensors. And then as far as the y-axis values, this is the percentage of the contrast that actually gets resolved by the image sensor for a given spatial frequency. So anything between 0.8 and 1, you could consider that excellent. Anything between 0.6 and 0.8, you consider that good. Anything between, say, 0.4 to 0.6, you could call fair. So if we take a look at this, we are doing really excellent in the coarse detail category. And then out to about 60, we're still doing excellent, very good for medium detail. Our fine detail, all the way out to, say, 120, I would say we're very good to good. And then we transition into more of the fair range as we hit the sensor Nyquist. So all over, this is an excellent result for a Cooke triplet. We're getting great performance, and I'm happy with our design. However, there are more modulation transfer functions than just the central one. Let's take a look at some of the farther fields. So this is would be this dot here, which would be out a little bit over here. And we can see we're still getting a clear point spread function, and our modulation transfer function is roughly the same. So I'm happy with that. Now let's go out to more of the edge of our detector. And you can see we're starting to lose some of the crispness that we used to have. Nevertheless, the MTF is still looking pretty good, even as some of the aberration is creeping in here. And if we go all the way out to one of the far corners, we can see that it's gotten a lot worse, and we can definitely see some coma in the point spread function. That's the kind of comet tail that we see going this way. And our modulation transfer function is noticeably worse. Nevertheless, we're still resolving a lot of our coarse detail and a lot of our medium detail with a strong MTF above 0.6. However, at the sensor Nyquist, we've dropped down below 0.5, whereas in the center we were, what was it, up around 0.6? Yes, we were up around 0.6. So you can see this does definitely decay as you go farther out towards the edge of the sensor. At this point, we've completed our design. To recap, the first thing we did is we did some rough calculations to figure out the diameter of these lens elements. Then we went ahead and created them with placeholder curvatures. We built a set of paraxial analyses and ran a paraxial-only optimizer leveraging its speed to get an approximate solution to our optical system. We then created a suite of ray tracing-based analyses and a ray tracing-based merit function, and then optimized that to fine-tune our design. Finally, we verified our design by looking at the point spread function and the modulation transfer function in both the near and the far field. And that's all for this video. Thank you very much for watching, and I will see you next time.